This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 6, Lesson 8, Humidification and Moisture Equipment. Cold outdoor air carries almost no water, and a heating coil adds none, so every hour of winter ventilation dilutes the moisture right out of your space. The handbook prints 3 humidification load equations, and they're really one idea with 3 different ways to get the dry air flow. We'll compute the fixed outdoor air form end to end, show the variable outdoor air form landing on exactly the same number, then meet the 2 moisture removal devices the handbook actually prints. Concept: why winter needs a humidifier. Air at winter design conditions holds almost nothing. Bring it inside, heat it to room temperature, and its humidity ratio never changes. You've raised the dry bulb and left the water content alone, so the relative humidity in the space collapses. That's the whole problem. Infiltration and ventilation keep swapping moist indoor air for dry outdoor air, and the humidification load is the pounds of water per hour you have to inject to hold the indoor humidity ratio against that dilution. 3 things set it: the humidity ratio difference between indoor target and outdoor air, the rate at which you swap dry air, and the moisture the space already makes or loses on its own. Setup: 3 printed forms, 1 idea. The handbook gives 3 equations for the humidification load, and they differ only in how the dry air flow is described. Form 1, natural infiltration. Density times space volume times air changes per hour times the humidity ratio difference. Form 2, a fixed quantity of outdoor air. 60 times density times the outdoor air CFM times the humidity ratio difference. Form 3, variable outdoor air. The same product on total flow, scaled by a bracket built from the indoor, mixed, and outdoor temperatures. All 3 then subtract internal moisture sources and add other losses. Pick by what the problem hands you: an air change rate on a volume, a fixed outdoor air CFM, or a total flow plus a mixed air temperature. And note what isn't printed here. The handbook lists no humidifier types at all, only these 3 load equations. Setup: the where list. Read the symbols once. Load is pounds of water per hour. Volume in cubic feet. Infiltration and air changes per hour. Both flow rates in CFM. The humidity ratios are indoor and outdoor design conditions, in pounds of water per pound of dry air, not relative humidity. The 3 temperatures are indoor, mixed, and outdoor. Internal sources and other losses are both moisture flows in pounds of water per hour. And you don't look the density up. The where list hands you 0.074 pounds per cubic foot at sea level. Worth noticing, because it isn't the slightly different air density buried in the sensible heat factor you've used all course. Solve: the fixed outdoor air form. An office air handler pulls 4,000 CFM of outdoor air at winter design. Indoor humidity ratio is 46 10,000ths. Outdoor is 11 10,000ths. Internal sources are 8 pounds an hour, other losses 4. Dry airflow: 60 times density times 4,000, 17,760 pounds of dry air per hour. Multiply by the humidity ratio difference of 35 10,000ths, 62.16 pounds of water per hour. Subtract the internal sources, add the losses, 58.2 pounds of water per hour. That number is the humidifier capacity you actually specify. Solve: the variable outdoor air form, same building. Now you're given total flow and a mixed air temperature instead of an outdoor air quantity. 16,000 CFM total, 70 inside, 55 mixed, 10 outside. The bracket is 70 minus 55 over 70 minus 10, 15 over 60, a quarter. Dry air flow on total is 71,040 pounds an hour, times the humidity ratio difference, times the quarter, 62.16. Subtract sources, add losses, 58.2 again. Identical, and here's why. A quarter of 16,000 is 4,000 CFM of outdoor air. That bracket is the outdoor air fraction. Take the mixed air temperature relation, set the return air at the indoor condition, and it rearranges into exactly this ratio. That's your algebra across 2 printed relations, not something the handbook prints as an identity. Concept: desiccant dehumidification, the reverse problem. Summer flips the question. Too much moisture, and you'd like it out without chilling the air below its dew point. A desiccant does that by sorbing water straight out of the airstream. Now what the handbook actually gives you here is one psychrometric figure and nothing else. No equation, no performance factor, no regeneration discussion. So read the figure. The process runs from state 1 to state 2, down and to the right, along a line labeled constant wet bulb. Humidity ratio falls while dry bulb rises, because the latent heat that water was carrying reappears as sensible heat in the air. The air leaves drier and hotter, which is why a desiccant stage is normally followed by sensible cooling. And that is the exact mirror of the evaporative cooling path from week 1, which climbs up and to the left, along the same constant wet bulb line. Concept: evaporative moisture equipment. The handbook's evaporative air cooling section has exactly 2 pieces, and both are effectiveness ratios. Direct evaporative air coolers get a direct saturation efficiency, how far the leaving dry bulb approaches the entering wet bulb as a percentage. Week 1, Lesson 7, works that one end to end. Know where it lives, don't rederive it. Evaporative dehumidifiers get a performance factor, the actual air enthalpy change over the maximum air enthalpy change. A performance factor of 1 is the ideal. The unit cools and dehumidifies the entering air to a wet bulb temperature equal to the leaving water temperature. So with entering enthalpy 42, actual leaving 34, and ideal leaving 32, 8 over 10, 0.80, 1 subtraction each, then divide. Traps. 4. 1. Only the CFM forms carry the 60. In the infiltration form, volume times air changes per hour is already cubic feet per hour, so there's no 60. Slip 1 in and the load lands 60 times high. 2. The signs are minus S plus L. Internal moisture sources are water the space already gets, people, cooking, processes, so they subtract from what you must add. Other losses add. 3. The density here is the one the wear list prints at sea level, not the air density hiding inside the sensible heat factor you've used all course. Read it off the wear list every time. 4. The bracket is an outdoor air fraction, not a temperature correction. It scales total flow down to outdoor airflow. If the problem already gives you the outdoor air quantity, use the fixed form. Applying the bracket as well counts the mixing twice. Quick recall. 3 humidification load equations, 1 product. Infiltration uses density times volume times air changes per hour, no 60. Fixed outdoor air uses 60 times density times the outdoor airflow. Variable outdoor air uses total flow times the outdoor air fraction bracket. All 3 multiply by the humidity ratio difference, then subtract internal sources and add other losses. The density is printed for you at sea level. Desiccant dehumidification is a figure only, drier and hotter, down and to the right at constant wet bulb. Direct evaporative coolers get a saturation efficiency, which week 1 owns. And evaporative dehumidifiers get a performance factor. Actual enthalpy change over maximum. Golden rule: get the dry air pounds per hour right, and the rest is 1 subtraction, 1 multiply, then minus S plus L. Next up, Lesson 9, Combustion and Fuels. We put water into the air. Now we burn something to heat it. We'll cover stoichiometric air and the air-fuel ratio, why real burners run with excess air and what that costs you, higher versus lower heating value, and which one a rated efficiency is quoted against, and how a condensing boiler earns its efficiency by dropping flue gas below its dew point, recovering the same latent heat we spent this whole lesson adding. Everything's at peprepengine.com, cheat sheet, worked solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at peprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.